So welcome back to Zoom, Math 332 class. Last week we started some tests based on the chi-square random variable. And we have another one. Today, some parts of this will feel similar to the one we just did, which was comparing k proportions, although the context is a lot different. So let's take a look. Section 7, just moving on through chapter 13. The title is Contingency Tables. And so let's just read. Members of a population are selected at random and measured according to two attributes. The question that we address here with contingency tables is, are those attributes independent? So when I was an undergraduate student, I ended up at a school where I finished my bachelor's degree, and some people I ran into at that school were pretty critical of small high schools, and in particular, students who came from small high schools. They were of the opinion that small high schools, they didn't prepare students well academically. The students weren't prepared socially. That is, the sort of conventionality, maybe provinciality, I should say, of a small school didn't really play well at a bigger school. And so just a lot of negative feelings I ran into from people that I was taking classes with that were, my friends and classmates at this college. And it kind of made me mad because I was from a super small high school. I think probably we had about 60 in 4 grades, freshman through senior. I think we had 18 in my graduating class. So definitely the definition of a small class. And I felt like I was as ready for college as they were. And so, like I said, it just kind of made me mad to hear them talk that way. So to put in the context here, the population, maybe if I were going to study it, and I did, more on that later, that I'm interested in are college students, in particular college students at the college that I chose to attend. And then we do a random sample, we select a student, and we measure them according to 2 attributes. In my case, the first attribute maybe would be the size of school they were from. And while that could be, a wide range of integers, for the purposes of this test, we would split it into some categories. And let's just say small, medium, and large, and we could worry about how to define those later. And then, how are we going to measure success? Well, one way to do it is by GPA. It's a numerical, and so we'll measure the size of high school and as well as the GPA the students were earning in college. And then we ask the question, are those independent? Does it matter? Is there any relationship between size of high school and GPA in college? So that's the idea here. So we go off, we conduct a random sample, and we see if we can find a way to test it. Like I said earlier, maybe the chi-square random variable will be involved. This is more than just a hypothetical example. At that school, a requirement for graduating in most STEM majors was to do a senior thesis. And I guess I was worked up enough about the things that people were telling me, my classmates, that I chose to do exactly a contingency table test on the data. So in a long sequence of starts and stops, I was eventually able to get access. I was declared an employee of the registered office, albeit unpaid. And that got me access to actual student records. I try to have students self-report, and it's like everybody had a 4.0 GPA. And I was pretty sure that wasn't true. And so eventually I was able to get hard data, the student records in the registrar's office. And so I actually added a third attribute. Not only did I look at the size of their high school and their college GPA, I also was able to include their high school GPA. So I took the test we're going to describe here one step further, we're not going to do that. We're just going to talk about a two-way contingency table. If you look at the section 7 in the book, they call it an R by C. You'll see the variables in just a minute. A two-way contingency table, and that's all we'll focus on here. And part of the problem when I was a student was Excel hadn't been created yet. And so a very real challenging part of the problem was to do the calculations. And as an undergraduate, I was required to take Fortran programming as a math major. And so ended up writing the routines in Fortran, not just to facilitate calculation like we think about these days, but it actually was a pretty challenging part of the project. And in the end, I was able to come up with some conclusions. It's funny, as emotional as I must have been about it then, I don't really remember. I have the report on the shelf in my office, so I could look it up if I need to. But that's the idea. We have a population. We could think of 2 attributes for every member of that population. They need to be things that are measurable. The example I gave you, they were all a numerical on a sliding scale, which means we have to kind of arbitrarily choose where to break the categories. I chose, small, medium, and large. I didn't decide where those cuts would be. When I did it back when I was an undergrad, I had to decide, what's a small school, what's a medium, and so on. A lot of times we can talk about, maybe the kind of car a person drives versus the zip code they live in. So those would be, non-numeric. Zip code's numeric, but it's not really a number, it's an identifier. And then the categories would be much clearer. We could still do this contingency table test on that. So it's flexible enough to allow the possibility. So how do we do it? Let's get into the details. They're on the other panel over here. So we're going to test the hypothesis, the null hypothesis. The 2 attributes. If I, this is a generic form of a hypothesis. If I had a specific one in mind, I would list them out there on the null hypothesis. I wouldn't use the vague pronoun they. But we will here, and then when we work problems, we can fill in the details. And the alternate is just simply that they're not independent. So the null hypothesis, they are independent. Knowing one of them tells me nothing at all about the other one. Or maybe that's not the case. Telling me one of them tells me something about the other. So what we're going to do, of course, next is to test the hypothesis. We need a random sample. So we'll go out and identify members of our population as identified in the null hypothesis. We're going to measure each one according to each criteria, and then we're going to plug them into the cell. So here's attribute 1, here's attribute 2, and every member of the population of our random sample, we measure the 2 attributes, and they go into a cell somewhere. And we're going to label the contents of the cell. This is based on our random sample. Remember in section 6, F represented frequency, it's a count. And we'll do the same thing here. So Fij is the number of sample items that end up in cell Ij. And then we're going to need some row and column totals. So we're going to use the notation Fi dot to be the total that land in row I. So F1 dot would be the total that land in the first row here on down to row R. And similarly, F dot J will be the total in column J. And then we'll let F with no subscripts at all represent the grand total, which in previous sections we would call N, or sample size. So certainly the sum of all of the values in that table add up to F. The sum of the Fi dots add up to F. The sum of the F dot J's add up to F. Every sample member is in exactly 1 row, exactly 1 column. So all of those things are true. Okay, so let me pause this while I convert the board for what we're going to do next. Just a second. All right, so previously we defined our frequency notation, and now we'll look at some probabilities. So we're going to define theta I dot to be the probability that a sample value lands in row I, and theta dot j, probability of landing in column J. So use the dots just like we did for the frequency measures. And then we can estimate those thetas. Theta I dot is going to be the total number of sample elements in row I divided by the total number of sample elements. Similarly for theta hat dot j, estimating the probability of landing in a particular, the jth column. And then if theta ij is the probability of landing in cell ij, so if you focus on like the probability of landing in cell ij, well, to land in cell ij, you have to land in row I and column J. So if you think of landing in row I as the event A and landing in column J as the event B, then landing in cell ij is A intersect B, right? To be in column I and column J is the event, the intersection, A intersect B. Now, we defined way back in what, chapter 3, that events are independent. Our definition is if the probability of their intersection is the product of their probabilities. And so since independence is what we're testing here, we want to know, is theta ij, the probability of landing in cell ij, is it the same as the products of landing in the individual row and column? And for theta I and theta j, we'll replace them with the estimator from our data. I didn't mention, we can estimate theta I by counting, maybe I did mention it, how many land in row I divided by the total number. I did mention it earlier, still the same. And so then, before we defined our frequency variables, and now we want to talk about how many do we expect? Well, under the null hypothesis, the expected value in cell ij is the probability of landing there times the total number of items in the sample. Well, under the null hypothesis, theta ij is theta I dot times theta dot j. The probability of the intersection right here is the product of the individual probabilities. And to get the expected value, we multiply that probability by the number of sample elements. And then if you replace theta I dot and theta dot j with these values, then we get this guy right here. Circle it. So that's the expected number in every cell if the null hypothesis is true. Just the total in row I times the total in column J divided by F, the total. All right. So we have language that's a lot like the language we developed in chapter 6. We have the frequency measures, we have the expected. Just like we did in chapter 6, we can normalize the number we would expect in each cell into a standard normal, and then we could square, we get a chi-squared. And so what we're going to do is exactly like we did in section 6. For every cell in our table, 1 to R, 1 to C, all of them, we're going to find the expected value minus the frequency. If the null hypothesis is true, this should be a very small number because we would expect the same, about the same number that actually showed up. If the null hypothesis is wrong, then in some of the cells, there should be a big difference here. But they're not independent, so there's not a relationship, and we would expect big contributions. Every single term, so for every cell in the table, we get a positive contribution. If the null hypothesis is not true, we expect bigger ones. So as we move over the table from cell to cell, we are accumulating. Think of this as sort of error in a form that we can measure through the standard normal squared through a chi-squared. So we find the error here and we accumulate it as we go. These are all positive. And because of what I said earlier, relating it back to standard normal, normalizing and such, we can think of it as a chi-square random variable. So we're just accumulating these differences, modified so we can measure, so they have a chi-square form. And we end up with the total. We make it all the way around our table, and let's just call that random variable x. And based on the same reasoning in section 6, we can think of that as a chi-square random variable. I'll say more about this in a minute. For right now, let's just say the degrees of freedom are the product of the rows -1 and the columns -1. Okay. We'll give you a partial justification for that in a minute. Remember, I said last week that degrees of freedom are complicated. In fact, the authors of our book would say that some of the issues are beyond the scope, as we need to dig deeper, and the author gives us some references at the end of the chapter where, if you're curious, you want to find out what's going on, you can look into some of those references. All right, so we're accumulating these errors, big errors, when the cells don't satisfy the independence. We have a chi-square. And then if we want to test our hypothesis, we can compare it to the official chi-square value for a pre-specified alpha and the degrees of freedom. Or we could use a p-value, which in Excel is just chi-dist, with our stat and our degrees of freedom there. All right, so a word about degrees of freedom. And then we'll run the test. So here's the result that we need to dig into those references at the end to fully understand. In fact, maybe even to begin to understand. But here's what we're going to use. For the test we're doing right now, the number of degrees of freedom, I'll abbreviate, DF, is S minus T minus 1, where S is the number of terms in the sum in our chi-square, and that's just R times C. T is the number of parameters replaced by estimates. Remember, we talked about that for our K proportions. Okay, so let's think about that for a minute. In a sense, you might think we replace all of the thetas with our estimate here, theta hat, theta I dot hat, or theta dot j hat. But those are not all independent replacements, because we know that the probabilities for every row have to add up to 1, and every column they have to add up to 1. And so if I knew all but one of them, I could calculate the other one. That is, if a sample element landed in row 1, then he's either in column 1, column 2, up to C, guaranteed. So if I sum up those row probabilities, they have to add to 1 because he's in one of those columns. But if I knew all but one of them, I could then add them up, subtract from 1, so I could get the missing one. So we're actually only replacing R minus 1 row probabilities and C minus 1. And therefore, T, the number of replacements, is R minus 1 and C minus 1. So I've explained S, I've explained T. 1 is 1. So the total degrees of freedom is RC minus R minus 1 minus C minus 1 minus 1 more. This is RC minus R minus C plus 1, which conveniently factors. So that is the explanation for the degrees of freedom associated with that chi-square over there. And it's a nice way to think about it. We'll just take 1 away from the rows and columns and multiply. That's our degrees of freedom. Let's do an example. I have picked one out. Let me pause this while I set it up. All right, we're going to work through problem 77 on chapter 13. I'll just read it to you. Tests of the fidelity and the selectivity of 190 radios produce the results shown in the following table. And there we have the table shown. So our population is radios. I assume radios that are similar in nature. And there are two aspects to these radios. One of them, the author calls fidelity. The other one calls selectivity. I don't know what those mean, but whoever did the sample, they knew what they mean, and they could put them in boxes accordingly. So just like we did before, I'm going to work through this in Excel. So let me share my desktop and show you the spreadsheet. All right, so here is the raw data. This is problem 1377. And I didn't identify which attribute is which. I don't suppose it matters. The columns are fidelity. So let's write in fidelity over there. And I don't really have a place to write selectivity. We'll let fidelity identify what we need. All right, as you can see the sample data, notice we had not a single data value over here. I failed to mention earlier, remember, this whole chi-square idea is based on approximating a binomial with a standard normal. And we have conditions on when that's okay to do and when it's not. A binomial, can be far from symmetric if n or theta are extreme. And so we've been saying that we can use the approximation standard normal for binomial if the expected number of successes and failures are both bigger than 10. The author for this technique uses 5 for that, and we talked that there's some issues there. We're just going to go with 5. That's what the author is using. So these are the observed frequencies, and so we don't really care how many show up there. There's no theory result. But when we calculate the expected ones, which we'll do in just a minute, if any cell has fewer than 5 expected values, then our test loses validity. And so we would need to collapse the rows or the columns by 1, whatever seemed to be the best way, so that every cell had at least 5 members in. Okay, so we'll take a look at that. So here's my raw data. And then over here, I have the expected. So these are the Fs. And then over here, the expecteds. We calculate them exactly like we calculated on Friday. That is, we take, you can see the formula. Oh, I'm wrong. I mean, we could do it that way. There's an easier way. The calculations we showed over here. The expected number of cells here is equal to the number of, remember, we're assuming the null hypothesis is true. So it's this 7, the expected number there, the 1, 1 cell, is the probability of landing in column 1 and also row 1. And we get that by multiplying the row and column totals and dividing by the total number. So there you see it. We have B7 times E4. B7 is the column total. And there I lost it. B over here. E4 is the 50 here, the row total. Now the dollar signs are just so I can copy. And, if you know how to use those dollar signs, then go for it. If not, then, you just need to write your 9 values over here one by one. Should do it fairly quickly. And I think I wrote the formula and copied it across there, and then we could copy that down, and that was the quickest way to fill in these expected values. Oops, happens to be a wrong way. So let's cancel that out, and then we can copy this down. So copy it down, and then you have to change some references. There is a way to just plug the formula in on 15 and copy the whole thing out. I'll let you worry about that. You're probably better at it than I am. Or like I said, you could just do 9 different calculations and get the expected values here. Notice that all of the cells have are bigger than 5. Let's get rid of some noise here. Oops, wrong way. There we go. They're all bigger than 5, and so we don't need to collapse any rows or columns. And we can see we're getting pretty good evidence that the null hypothesis is not going to work. We got 0 in cell, 3, 3. We expected to get a little over 7 elements there. So anyway, the next thing we do is we add. We get our chi-square value. Those are the expected values, and now we get our chi-square. Did the work earlier. And there they are, and this is where we take the expected minus observed, we square it, and we divide by the expected. So just like we did up here, you can use, actually you can write the formula there and just copy it. It'll read the right cell. Copy it all the way over. It doesn't want to do it for some reason. So drag over the whole thing. And then we can drag that over to the right. Perfect. So these are the individual chi-squares. You can see the one we talked about before where we had this big discrepancy, 0 and 7. We get that's our biggest contribution. Oh, I'm wrong. There's a 25. So we got 31 in this cell, and we actually were only expecting just under 13. So big discrepancy. I'm thinking the null hypothesis doesn't look like it has much of a chance. We add up the values, all of the chi-squares overall, every row and column cell, and we get 52.7. Now, we don't know how to read chi-squares like we do in standard normals or even Fs, but 52 feels big. And I did a quick p-value calculation. You can see it here, chi-dist, G15, our chi-squared value there, 52.7. And we have 4 degrees of freedom. We lose 1 from each row and column, turns the 3s into 2s. 2 times 2 is 4. And you can see the p-value was negligible. Let's look up the critical value. I could look it up in the book, or I can use Excel. I'll do it down here. So here I think it's chi-inverse. If we use 5%, and we have 4 degrees of freedom. Let's turn that parenthesis around. So we only had to be 9.5 to reject the null hypothesis, and we're all the way out at 52. So you can see I rejected with 3 exclamation points. Maybe that's not quite enough. We'll add a few more. All right, and that's how we do an R by C contingency table. It seems the calculations are so simple now. It seems kind of weird that my project back in, it would have been in 1976, that writing a Fortran program to do the calculations was a major part of the project. And like I said, it was 3-dimensional, not 2, but still. there are also lots of different tests I could do. That is, I could pull all the two-way tests out of those three-dimensional data, and I could do one three-dimensional that all three of the attributes were independent of each other. And once the data was in there and the program was written, that was pretty easy to do. Here we just have one test we can do. We did it. We reject the null hypothesis. So I will post, this is the lecture for Wednesday, April 8th, I guess it would be. And sometime before the end of the day on Wednesday, April 8th, you should have a problem or two added to the homework. So happy computing. We'll talk to you later. Goodbye.